So today we're going to talk about getting back to the fundamentals of real-time analytics, and we're going to talk about how the latest integration with Apache Doris and VeloDB is Apache Iggy, which is going to help people achieve greater freshness and lower latency as we get real-time data into an environment that can serve real-time analytics. With me today, we have Kranti Parisa. Pranti, would you like to introduce yourself?
Yeah, thanks, Kevin. Hey, everyone, thanks for joining. And this is super fascinating story that both Apache projects are coming together for powering the next generation of streaming analytics. So myself, founder CEO of LaserData. So LaserData is an infrastructure company for AI native systems, as well as the traditional event-driven architectures. So the Apache Iggy is donated by us to Apache Foundation. And before LaserData, I was leading engineering teams at Apple and as well as Dialpad as well. And I'm a long-term Apache contributor, contributed to Lucene and Solar as well, and also co-author of a couple of books as well. So welcome again.
Thank you for joining us, Kranti. Brief bit about myself. If you haven't attended a webinar before, I lead product in the US, focusing on a lot of our go-to-market effort. Had the fortune and opportunity to work on various big data projects, as well as leading the development of Watsonx data and Watson Query when I was at IBM. For today, I'm gonna go through. So let's talk a little bit about the project first, and then we'll do a quick recap on Apache Doris and VeloDB.
Yeah, so Apache Iggy is a next generation streaming engine built from the ground up using Rust. So this is not like a next generation of Kafka kind of infrastructure, but this is in the similar lines of Kafka from the principles point of view, but it is rethought from the ground up in terms of the architecture behind it, and the streams and topics and the abstractions on top of it are also rethought from the ground up. And some of the architectural choices that we have made, we will go through them later in the presentation. And not just on the details of Rust and why it makes it faster than Java, GC, JVM systems, but that excitement has started showing in the community. As you can see, we have 700 plus members in the community, 100 plus contributors actively contributing to various parts of the system. A lot of connectors have been built as we speak now, and we are very proud to say that we are a number 3 project in terms of the number of issues and PRs merged and so on and so forth under Apache for Rust ecosystem. And we have like 4,000 stars, organically grown the community as well. We have a lot of protocols built, not just the TCP, but we also have Quick, and we have done a lot of work on WebSockets as well, because ultimately we want to use the same system on the edge to the server message streaming also, because if you think about Kafka, it is only server to server, right? So we want to have a single system which can work between server to server, edge to the server, and also we're building agent to agent communications protocols also, and a lot of SDKs available on all the major programming languages as well.
No, thank you for the brief introduction, and we will get into a lot more detail in just a second. As per usual, I'm going to do a quick recap of Apache Doris and VeloDB, the company that I work for. Apache Doris, like Apache Iggy, is a top-level project, graduated in 2022. Also, a really vibrant community with over 700 plus contributors, and it's generally widely adopted. And Apache Doris is a real-time search and analytic databases. And I'll go through a little bit about all the different workloads that it can cover and where it sits in the data stack in just a second. With Apache Doris comes with the commercial arm, and that's VeloDB. It is really created by the creator of Apache Doris, really to offer a commercial arm for those who wanted a bit more support and also being able to run this enterprise skills without having to acquire years of expertise, leveraging the capability. It's backed by $140 million Series A raise with a lot of the committers and the PMC members as part of the company, and we do have offices globally. So if you're interested, please check us out, and you can get a free trial as well if you're curious about the product. A little bit background about what we do. So as we're talking about real-time analytics, really the fast in and fast out, the fast ingestion versus the fast queries. VeloDB and Apache Doris is a real-time database. Has two components, a query engine that allows you to get exceedingly fast queries on retrieval up to about 100 milliseconds of latency. And this is the number that a lot of real-time analytics will quote, right? The respeed. However, what's unique about VeloDB and Apache Doris is that it also have a storage engine here, right? And because it has a storage engine, it's also able to take the data from a sync connector, such as the one that we built with Apache Iggy, and write that data into the data store very quickly at the same time that you're reading. So not only you're getting fast reads, but you're also getting high freshness as well as high throughput of data that are coming through. So things like high concurrencies, complex joins can be handled in real time with low latencies due to a lot of the indexes and optimizations we have introduced. Also, if we kind of go from the top, it is interoperable and very friendly for usage no matter where you're trying to perform your analytics, whether that's through traditional JDBC, ODBC, or you're trying to connect with MCP, or you're just having your agents load our skills and interact with the CLIs so that you can do analytics directly. It is fully MPP query engine, fully vectorized with columnar stores. So really, really quickly, all the modern goodness that you get from a massive parallel processing engine, as well as a robust workload management systems with isolations and such. Some of the things that people don't know frequently is that we also have a row store as well. So if you have workloads dealing with point lookups that require exceedingly low latency, there are additional ways that you can leverage those capability as well. But for the sake of analytics, most people use columnar stores with Apache Doris. It also integrates with Lakehouse. So if you have data that are scattered through open data lakes, CDC sources from transactional places, streaming sources from any of these places, including now Iggy, we can pick that data up and allow you to analyze that data very quickly. And of course, we support integration with upstream tools as well. So for things like data agents, traditional BI, your application layers, or observability, we offer integrations with those upstream tools as well. So if there's any questions, happy to take them at the end of the presentation specifically about Apache Doors, but I'm going to continue the presentation on the integration for how we're going to deliver additional freshness and lower latency through the integration with Apache Iggy. And it really comes down to the thing that I mentioned earlier, right? When we look at high freshness and real-time data, often we only focus on read. For those who may have been looking at some of the press releases or attended the Databricks Summit, there's a huge keynote about real-time. Yet at the same time, the only number that were mentioned was read numbers. However, equally as important about being able to read the data quickly is actually getting the data into a place where it can be read and used for analytics. And that's where the upstream ingestion, streaming, and the ability to write data into data store comes in. So in this case, Apache Iggy offers ability to write data at the single digit millisecond level, and we're able to address a lot of the problems that also cause this streaming stack to break. Because often when we say, oh, just use CDC streaming, we often end up spending more time on those data pipelining tools, on those streaming tools, trying to make sure that it's stable, it's robust, it doesn't break, instead of actually focusing the time on the analytics and generating alpha, basically trying to figure out what are the potentials that can be used for decision making to improve to actually drive business. Some of the things that have issues with traditional analytics in terms of streaming could be ingestion backups, right? Any latency at anywhere from this end-to-end perspective cascades downwards. So if you have a spike in latency on the streaming side, all of that propagates. As I said earlier, managing that middle part gets cumbersome. There are separate clusters, separate compute resources, multiple components, stages, and not only adds the latency with the additional hops, but it also becomes very cumbersome to manage. And then finally, once the data actually arrives at a database, is it actually going to be able to be used right away? With traditional lakehouse analytics or lakehouse analytics in general, which is hot, there's two ways that you can get data written, right? One is merge on read. Fastest way to write the data. Everybody's saying you can write these data into a lake, into your target store very quickly using the append method. In fact, most of the real-time engine uses that append method to be able to write quickly. However, you pay the tax when you read the data. There are metadata that you have to merge, and if you don't regularly clean up and merge these smaller files that are being appended, or you're dealing with latency on the metadata merge, there is a theoretical maximum in terms of which certain minimum of latency that you can achieve due to these things. However, with Apache Doris, there was a lot of integrations to really speed up the ability to write the data into the data store as well as reading it at the same time. A lot of this I mentioned earlier through the clever indexes, bucketing, but the biggest one has to be really about merge on write, which we'll go through in a little bit. But again, just kind of skipping through this a little quickly, just to give you a view of what this looks like again from an end-to-end view of where the data is being produced to where the data is being landed. So we have the producers, which could be any of your applications, your transactional sources, or IoT devices that are generating data. And then Apache Iggy handles the movements. And then we together created the Rust sync connector that allows us to take the data from Iggy and then write that data into our data store very quickly. And if we're looking at end-to-end latency, we're looking at about a 1 millisecond write latency on the Apache Iggy side, and then a less than a 1 second end-to-end freshness if we look at everything end-to-end. And then also onto the merge on write component that I mentioned earlier. The reason this is unique is that as you're writing the data into Apache Doris, instead of writing metadata files, we write a bitmap instead using a unique key model so that instead of merging all of the files, you only have to merge a bitmap, which is much smaller amount of data, enabling you to be able to query that data and write at the same time without a lot of degradations in terms of your read latency, which you will encounter in methods such as merge on write. However, people say, well, copy on write sort of fixed on the retrieval side, but you pay for that when you actually write the data because now you're writing a much bigger file. You're going to spend more time writing the data. So there is latency on that particular side as well. So that's the high level of what we've created together to help people get fresher data with higher throughputs. But, with all things performance, everybody's wondering how fast does it go and where does the speed come from? So the last thing I'm going to say is here are the high-level performances comparing Apache Iggy to Kafka. And as you can see, we're able to offer with Iggy much higher throughput, which is really important when it comes to streaming, as well as a much lower latency, and in some cases, orders of magnitude lower. 30 times lower when we're looking at the lower 99.3 tails in a 3 times higher throughput, which is quite impressive considering this Apache Iggy is super lightweight and easy to operate as well. So now I'm going to hand over to Kranti to take us through all the gory details.
Yeah, thanks, Kevin. Do you mind going back to the previous slide for a second?
Mhm.
Thank you. Yeah. So as Kevin said, these are not thrown numbers. These are benchmark numbers. So we have taken a real world payloads of what streaming analytics look like. And then our teams have produced a benchmark and it's available on VeloDB GitHub repository. So there is a GitHub repository, VeloDB demos, and you can actually see there is a Iggy benchmark and there is also a Kafka benchmark as well. So as you can see here, the main thing is it's the same hardware. So this is not like, running on a local machine. We have taken AWS instances, the real EC2 instances that the production loads would run. And then we basically initiated the load from one EC2 instance into the other EC2 instance where Iggy is running, and then into the VeloDB Cloud, where so that like the data streams into the AWS infrastructure, through the AWS infrastructure into VeloDB. And as you can see here, why Iggy is fast, and it is insanely fast. And the key thing, if you have not noticed, the latencies between P50 or averages and P999 is not hugely deviating. Unlike the other systems, you'll see a huge number of spikes because of Java GC pauses and so on and so forth. And in my experience, working at Apple and other major companies, we used to throw more hardware at the problem so that we can smoothen the curve and get the latencies manageable for the business requirements. But we don't need to do all of that stuff. Fundamentally, Iggy solves that problem at the tail latencies, and to be very consistent tail latencies. It's not going to be huge spikes, as you can see. And the critical aspects there, maybe you can go to the next slide. There are a lot of architectural choices that we have made that made this difference. Apart from being Rust itself, the language itself is giving us powerful, secure, and machine level performance without the garbage collections and overheads that other systems have. But we haven't stopped there. We were so obsessed about the latencies and efficiencies of the systems, especially the tail latencies. That's what we want to really solve the streaming problem. So we have implemented architectural ideas like thread per core architecture. So I'm not going to go into too much details of it. There is a blog post that we have written on Apache Iggy website. So if you go to iggy.apache.org, there is a blog section. So you should definitely check out a few of the blogs. Very, very interesting reads. The core idea is if you leave the computations to the machine, the tasks jumps between the cores. And what we have achieved is okay, let's just pin one thread per core so that there is no context switching. There is no metadata passing between those when one core is busy, and then the incoming request needs to be served by the other core, and so on and so forth. So that's the thread per core architecture. And we have also implemented IO U-ring. This is how basically you handle IO, async IO. We have tried a few Rust libraries, and then we have implemented comp.io. It's a Rust library for async IO, and we have implemented WebSockets inside it because we want to support the WebSockets protocol also, like earlier I said. So overall, the choices of how you handle the disk, because it's a persistent log, right? It needs to be persisted, and a lot of the tail latencies will impact how you handle when you're writing to the net, through the network and to the disk, and how you handle CPUs, how do you handle RAM, and so on and so forth. So IO U-ring, thread per core architectures, Rust is giving us foundation for it also. And we also worked on so many other optimizations, like we skipped page caches and so on and so forth. So very interesting ideas. Please check out the blog for more details. But that's where the core performance comes, where we are taking full advantage of the modern hardware, squeezing to the maximum possible, because why not, right? So we are paying for the machines in the cloud infrastructure, so we should make them work. So which basically gives us order of magnitude efficiencies in terms of throughput and also latencies. So if you go to the next slide. So that's the high level details about what we have done with Iggy. The connectors, as Kevin mentioned, our teams have built a Rust native connector for Iggy to Doris. So that is another major thing. So it's all one binary with Apache Iggy. You don't really have to deal with huge infrastructure setup and complex operations like other systems. So it's very simple to run. The connectors are also embedded. You have very similar to Kafka Connect. We have a connectors ecosystem, but it is natively binding into the server itself, so that the overloads are really, really very minimal in that sense. And that's where the performance comes that you saw 2 milliseconds, 3 milliseconds at P999, even at a very high workload on a cloud infrastructure as well. So if there are no questions, maybe I can take over the screen share and show the demo.
Awesome.
All right. Let me know when you see the screen. Do you see the screen?
Yep.
Okay. So before getting into it, very similar to what Kevin was trying to mention about VeloDB, the offerings on top of Apache Doris and so on and so forth, which is really powerful for running enterprise-grade infrastructures, right? So similarly, LaserData is the commercial company built on top of Apache Iggy. As I said earlier, we are the ones who created Apache Iggy and donated to an Apache Foundation. So we don't want to stop there. We don't want to stop being just a managed service for open source, engine. Even though that is the starting point for us, but we have taken the streaming infrastructure that we have built and extended that for the AI agent use cases also. What does that really mean? So I just want to spend a quick minute about the need for streams and why we think it is very powerful for building agentic infrastructures. So if you have multi-agent infrastructures right now, a lot of the data is getting transferred or transported using MCP protocols. I'm sure you heard about them. It is an amazing protocol for calling tools, but we have found practical at scale. It's very heavy in terms of exchanging data between them. So we came up with a protocol, open source protocol ourselves. You can check that protocol details at LaserData GitHub repository. So there's a repository called laser-SDK. Please go check it out. So the idea is, you make these agents exchange data through a stream. What is the advantage of that? You can transfer the data, low latency, like TCP, quick level protocols. It doesn't need to be JSON, RPC, HTTP protocols. And the most other important thing is, while these agents talking to each other through the stream, you can consume the same data for your secondary services in your infrastructure, like observability or analytics, for example, so that your orchestrator, the main agent who is delegating all these tasks, doesn't need to log into observability, doesn't need to log into analytics and so on and so forth, because all of these interactions are happening through a stream. Just like event-driven architectures, the secondary services are consuming from the same stream so that they understand which agent is sending what data to other sub agents in the system and so on and so forth. So, but when you think about agents, you need to have context, you need to have memory, state, and the graphs, and all these primitives that the agents require. Because let's say I have a master agent giving the task to the sub agents, and now there is a context change. The customer, is now asking a different question. Then the context needs to be propagated down to all these subtasks or sub agents who are busy executing these, these actions. They need to get the context really real time. And we solved this problem in distributed systems before, which is put the streaming in between and then stream the changes as quickly as possible. So that's what we did with the Laser SDK. Without going too much into the details, I'm gonna go into the demo now. So if you haven't registered for VeloDB Cloud, it's super easy. Where you can go and create a free tier, and then launch a cluster, create a warehouse, and then this is my setup. So in the interest of time, I have pre-configured a simple cluster. I have created it's tables. And then this is my server running on AWS, as you can see here. And there is a connection, string here, which we will use in a little bit. And very similar to VeloDB experience on the LaserData side also, the onboarding is very simple. You go to laserdata.cloud, just register with GitHub or Google account, and then you will land here. So once you create environments, which is like your production environment, your staging environment, your QA, and so on and so forth. So we have built extensive support for enterprise-grade features like RBAC, where you can control the access and so on and so forth. Let's just go ahead and launch the deployment. So right now, what's happening is it's creating the server on AWS, and then it is initiating these infrastructure. So we have designed it in a way that this is completely isolated, which means it's not in like a shared workspace. If you want to have in a shared workspace, you can run it within your own, bring your own cloud infrastructures. But we have designed it to be without having noisy neighbors in the infrastructure. So it's creating all of these Iggy instances, LaserData components on top of it, and then in a bit it should be ready. While it is preparing, so let's go here, and as I said earlier, I have been playing with this demo account, so I do have some data. Okay, so there's a bunch of data records sitting in the table. So basically, we are going to write into a stream, and the stream has a topic, and then we configure that integration between Apache Iggy and Doris through a connector, where anything written to the topic sits into Doris table, right? So if I just do some records, okay, there is some data here, right? So where like a bunch of agents are talking to each other and then exchanging data between them. So all of those analytics will be powered through VeloDB. Okay, so now this is initialized. So you can see all these names and the regions and so on and so forth. And then you also have connecting to the cloud itself. And then we have the stream UI, where you can look at all the streams. And these are the primitives that I was talking about. So we're not going to go into all those details now, because we are going to show the ingestion between LaserData and VeloDB. But you can play with all these stream UI capabilities for yourselves. So now let's say I'm going to create a connector, and then pick Doris. I'm going to say maybe 4. Create the connector. Just refresh. Okay. Okay. So configuring it now. So you can see there are a lot of details where I'm going to add a stream. So this is basically the pointer between these two systems, where the data is the stream name. And then let's pick and use the same table name as the topic. And then LD VeloDB consumer 1. Just give some consumer group name. Of course, you're going to enable. So now this is where you're going to configure the connection between these two. So I'm going to pick this connection string, enter there. So here as well, I have, as I was showing, I have created a database called LaserData. So let's just point to the same thing. So this is nothing but stream name is LaserData, database name is LaserData. Topic name is inference events _1. Create to the table also same with the same name. And then I have the admin Password on VeloDB side. All these settings are VeloDB connector settings. Okay, so I'm gonna configure that. Let's see if that's gonna work. And before, okay, so this is the amount of data. Then you can pick the connection string for LaserData because you need to stream the data into Iggy, right? So through the LaserData infrastructure. So we're going to use that. Let's say I'm going to replace this, right? So you can see, it's a Docker, it's a quick start producing, producer is producing into this endpoint with this credentials. Stream is LaserData, topic is this, and then I'm going to just, dump some sample data. Let's say, okay, so it's starting to write the data into Iggy now. So if you go to the streaming UI, you see the messages, should be going up as the data is coming from my Docker on my local into LaserData Cloud. And the same data should be appearing here. Let's see if we have configured the connector properly. Looks like not. Let's just go back. Okay, so we go to the connectors one more time. Okay, let's see what's happening here. So LaserData looks good. Maybe change this as well. Doesn't matter. I'm going to enable logs. Make sure there is no spaces here. Analyze the data, influence events, admin. I think this is all looking good. Okay, so okay, it's coming up now. 214, 200. Hmm. The data is being written here. Let's see. Okay, it's writing into LaserData's infrastructure properly. Okay, I think it's taking a little time, but you see the data is getting ingested there. Yeah, so that's the demo. And as I said, please go check out the Laser SDK. It's on LaserData GitHub repository. You can find all of these examples of how can you use this for agentic primitives. And as I said, please go to iggy.apache.org, go to blogs, read some of these blogs that we have put together. Hope you enjoyed the demo. That wasn't that bad. Okay, so now it's actually moving much faster, as you can see. 226, 900, 7, yeah, changing much faster now, which is what I've expected in the first place. All right.
Thank you, Kranti. It's always brave to do a live demo, especially in front of all these people. In the meantime, I took folks off of mute, so if anyone wants to come off mute to ask a question, submit a question to Q&A, please do so. I will take the time to address them as they come through. All right. Pretty quiet for today. Uh, in the end, let me just kind of make, oh, wait, we have a question that come through. Um, how it's a replacement for Kafka crafts. Um, Kranti, you want to take that?
Yeah, so if the question is this, is Iggy a replacement for Kafka? Yeah, you can, treat that as a replacement for the next generation of streaming infrastructure. Basically, if you want to have extremely low latencies, tail latencies, Iggy is built for it, for those kind of use cases. Kafka is an extremely rich ecosystem. If you need to have a lot of connectors and very high scale ingestions and so on and so forth, Kafka is still like a beast and it is amazing infrastructure. But Iggy is going to get there in terms of clustering for high availability. We are working on the clustering functionality, which is going to go out in beta in next, a few weeks or maybe a month from now. Uh, but it's a journey, right? So Kafka, as it stands today, was not built in a day, right? So it's a journey. So we have an amazing foundation, and even with clustering, I'm happy to report we have done few preliminary tests. So it's not going to be Zookeeper or those consensus algorithms. We have implemented something called view stamped replication (VSR) based consensus, and then the benchmarks that we have seen the tail latencies are not regressing too much, than the single node infrastructure. So, which is what we have expected and we have designed it for. So, yeah, long story short, is it a replacement? Yes, that's the journey that we are going towards. But LaserData is not just the streaming infrastructure, but it is also going to be the agentic infrastructure built on top of which Apache Iggy is not going to have all of those agentic functionalities that LaserData commercial offering is going to have. So if you need plain, ingestion infrastructure, message streaming infrastructure, yeah, go ahead and use Apache Iggy and please report where it's breaking, where it's working, and so on and so forth.
So there's a follow-up question. So how about the schema registry part of Iggy? Please
So we
share some
don't
insights on it for schema updates. Yeah.
Yeah, I was reading that question, Kevin. Thank you. So we don't have the schema registry feature at the moment. We do have these connectors and the data transformations. You can configure simple transformations of dropping fields or changing, changing the values of, based on business values and so on and so forth before writing into, say, Doris into the secondary systems, right? But then the schema side of validations and stuff, that is, community has been asking for it. We will get to that. We have been optimizing the most important bits of the system because that is what keeps us separate from the existing offerings. And all of these, schema registries, and all of these other very important features can be built on top of them. We just prioritizing the most complex and critical pieces of the engine first. But yeah, if you have ideas of how you used it with Kafka or some other systems, and if you have ideas of wait a second, this should have been done differently. This it's a good place to come and brainstorm some of those ideas. There is a Discord channel for Apache Iggy. Please join that, and ideas and contributions are welcome.
Awesome. I think there's another question, Kranti.
Yeah, any roadmap for making it pluggable with existing Kafka environment? Analogy, Data Fusion is query engine written in Rust, and Data Fusion comment gets plugin for Spark. Yeah, great question, Shaker. We are working on the Kafka proxy. To be very honest with you, we have started working on Iggy to be not another Kafka wrapper. So we have opted to not support Kafka protocol to start with, because that is very limiting in many ways. There is a lot of overheads in the Kafka protocol, which we don't probably need for many use cases. So we started off with a very fresh protocol for Iggy, and SDKs are super simple to use and so on and so forth. But exactly what you are asked for, a lot of community members are also asking for it, which is, hey, this is super powerful, extremely efficient. Is there any way for me to drop in replacement, right? So can I just point my code into Iggy and or LaserData and then start playing with it or testing easily than making a code change or implementations. So there are a couple of engineers in the community who have started working on the Kafka proxy initiative. Please go take a look on GitHub, issues for Apache Iggy. You'll see an epic of issues, bunch of subtasks in it, making really good progress there. So hopefully we'll have that soon.
Great questions. All right. Any other questions? Going once, twice. All right. Thank you, everybody, for joining today's webinar, and a special thanks to Kranti for sharing details about Apache Iggy and LaserData. Really, really looking forward to all the additional development that's coming down the pipeline as well. A couple of housekeeping items. Also exciting things to announce on the VeloDB side. We will be adding Apache Doris 4.1 into the enterprise version this month, and all the details will be shared in our next webinar at the end of this month. So be on the lookout for that. And Kranti, any last words on your end?
No, you said it all. Thank you, everybody, for joining us. And Kevin, thanks for the opportunity. It was fun talking about Apache projects, always. I loved it, when I was doing Lucene and Solar a long time back. And now we are building, the next generation of streaming. So very, very happy to partner with you guys.
Awesome. Well, everybody, have a great rest of your day, and we'll catch you on the next one. Cheers,
Yeah.
everybody.
Bye, everyone.